The domain of rational functions. So in general, we're going to follow these steps. We will factor the denominator. We will set the denominator, meaning each factor, equal to 0. Then we will solve for the variable. And these values are the values that are excluded from the domain. So for example, let's look at our first one, y equals x plus 4 over x minus 2. This is a rational function. Our denominator cannot be factored any further, so we are going to go straight to setting the denominator equal to 0. So x minus 2 equals 0. I'll solve for the variable by adding 2 to both sides. I get x is 2, and this is the value excluded from my domain. So my domain is any real number, but x cannot equal 2. Or in set notation, the set of all x values such that x does not equal 2. Or in interval notation, from negative infinity up to 2, union 2 to infinity. And our vertical asymptote is at that restricted value, x equals 2. Let's look at a second example. Y equals x minus 4 over x squared plus 1. So let's look at our denominator. We cannot factor this. Let's try setting it equal to 0. If I do that, subtract 1, x squared equals negative 1. Try square rooting both sides. I get x is plus or minus I. But with functions, we don't usually look at complex solutions. So for us, we have no excluded values. That means my domain is any real number. Or in set notation, the set of all x values such that x is an element of the real numbers. Or in interval notation, it goes from negative infinity to positive infinity. And I have no vertical asymptote for this function. Let's look at a third example. Y equals x plus 3 over x squared minus 4x plus 3. Okay, so let's look at our denominator. We're going to start by factoring it. The denominator factors to x minus 3 times x minus 1. Let's set these factors equal to 0. So x minus 3 equals 0. Add 3 to both sides. X equals 3. X minus 1 equals 0. Add 1 to both sides. X equals 1. These two values, 1 and 3, are excluded from our domain. So our domain is x does not equal 3 and x does not equal 1. Or in set notation, the set of all x values such that x does not equal 1 or x does not equal 3. And in interval notation, from negative infinity up to 1, my lowest excluded value, union the interval from 1 to 3. And 3 is my second excluded value, and then union the interval from 3 to infinity. And we have two vertical asymptotes here. X equals 1, x equals 3. These are both vertical asymptotes. Let's look at a fourth example. Y equals x plus 3 over x squared minus x minus 12. So let's start by factoring the denominator. The denominator factors to x minus 4 times x plus 3. So let's set the denominator factors equal to 0. X minus 4 equals 0. Add 4, we get x equals 4. X plus 3 equals 0. Subtract 3 from both sides, we get x equals negative 3. Those are our excluded values, so our domain is x does not equal 4, x does not equal negative 3. Or in set notation, the set of all x values such that x does not equal negative 3 and x does not equal 4. Or in interval notation, from negative infinity up to negative 3, our lowest excluded value, union negative 3 to 4, which is our next excluded value, union 4 to infinity. But this example is a little different because if you notice, we have an x plus 3 factor in our numerator, and it will cancel with this x plus 3 factor in the denominator. And we'll be left with the function y equals 1 over x minus 4. So the factor here that canceled, the x plus 3, does not give us a vertical asymptote. Instead, it gives us a removable discontinuity, also called a hole. So we only have one vertical asymptote for this problem. We have a vertical asymptote at x equals 4. And our other factor, the x plus 3 that canceled, leads to the x value of where we have a removable discontinuity. Let's look at one more example. Example 5. Y equals x squared minus 3x minus 4 over x plus 1. Okay, so our denominator cannot be factored any further, so let's set it equal to 0. Solving for the variable, I'll subtract 1 from both sides. We get x is negative 1. This is our excluded value, so our domain is x does not equal negative 1, or in set notation, the set of all x values such that x does not equal negative 1, or in interval notation, from negative infinity up to negative 1, our excluded value, union from negative 1 to positive infinity. But let's see if our numerator factors. It does, and it factors to x minus 4 times x plus 1. You'll notice we have x plus 1 in both the numerator and denominator. So those would cancel, and we'd be left with the function y equals x minus 4. So this factor of x plus 1 that we canceled does not give us a vertical asymptote. Instead, it gives us the x value of the hole, or the removable discontinuity. So for this example, we have no vertical asymptote. So in general, factors that are only in the denominator lead to vertical asymptotes, but factors in the denominator that cancel with factors in the numerator lead to removable discontinuities, also known as holes. All of these factors, whether they cancel or not, so all the factors in the denominator lead to domain restrictions.